So this is the final day for the theory for Chapter 5, Electrostatics, Day 6. We're going to look at one last example from earlier work with voltage and energy, and then we're going to look at a really neat thing called parallel plates, kind of an extra little topic that complements the four corners of the chapter that we've already done. So here we go. I mentioned we're going to do one example first from looking at voltage and energy. And it's this one here, and you may notice it's kind of out of number, right? You're like, whoa, the last example we did was example 1, and this one's example 3. Yeah, this in this chapter, we're kind of trimming things down a little bit this year, and this one's kind of above and beyond. Maybe I should put a little star by it and say, yeah, okay, there's something to think about if you want. The key thing about this question is that it is superposition. There are a couple of Q's out there that are going to influence this story. There's a Q here and a Q here, and they're already there. They're quite distant, right? If you add up all those distances there, 18 and 6 and 36, I don't know, was it like about 60 meters or so or something like that? They're pretty far apart. And what we're going to try and do in this story is move another charge from location A to location B. So there's a Q here, but I don't know how big it is, and I don't even know if it's positive or negative. And we're going to try to move it to location B. So the challenge is, if you did go and move it, what's the math going to do as you try to move this unknown Q from one place to another? So they tell you, oh yeah, it starts from rest. Okay, so no kinetic energy at the beginning. And they tell us it does reach B with some speed, right? Not a lot of kinetic energy there. And we did quite a bit of work trying to make that happen. Now, I'm actually not going to solve this question. There's not quite enough space here to do the whole thing, but I just want to show you what some options are. Okay, and then show you how that maybe it might be really good to actually work with voltage. So here's option number 1. You could say, well, why don't we do just good old conservation of energy and respect the fact that there are multiple potential energies at the beginning and at the end, because there are those two Q's that are already out there. So you could go K, Q, and that would be the 3.6 multiplied by, hey, maybe I'll do this in purple. Here's the Q we're looking for, don't know what that is, all divided by a distance there. That first distance would be 18, right? And then moving along, I don't want to put all the numbers in because there's not quite enough room. And then K, and then the Q, which would be the -2 microcoulombs. And then this mystery Q divided by how far we are away from that at the beginning. When we're at location A, we're 36 and 6 meters away, so we're 42 meters away, plus some work. And then in the end, we're going to have some potential and kinetic energy. So we would go K, the Q, which is the 3.6, multiplied by the mysterious Q, which we don't know when we're actually looking for. So I'm a little bothered by how many times this purple mystery Q is showing up. At the end, we would be 18 plus 6. We would be 24 meters away. There's another potential energy, and this is kind of the motivation for this question, right? Like, what do you do if there's so many potential energies here? The K, the Q, which is the -2 microcoulombs, and then the mystery Q, and at that point, we would be 36 meters away. Oh, and there's also some kinetic energy, apparently, 1/2 mv squared. Okay, they've just given you a value for that kinetic energy too, which is quite nice. So the goal in this story is to, through some arithmetic, to try to find this value, this single value for Q, which shows up in 4 different locations in the math. So just arithmetically, it's just really, really quite awkward. So that is one option. But option number 2 would be to rely on voltage. And you can actually tidy things up a fair bit if we go with voltage. So you could take the voltage from that first charge. You could take like voltage 1, multiply it by the mystery Q, add on voltage 2. So voltages just add up, just like energies do. You don't have to do any vector additions. You just simply add them up, times that mystery Q, plus the work. And you might say, oh, it doesn't look like it's going to be much shorter. No, but it can be a lot shorter. Voltage 1 at the other location. Okay, and then Q plus the second charge's voltage at that other 36 meter location plus that kinetic energy, which they just give to us. Well, I could put these two voltages together. I could just add those voltages up and just say, well, that's the voltage at location A multiplied by Q plus the work is equal to, and then add these two voltages together as well and go, okay, voltage B times the Q. Oops, that one should have been a purple mystery Q. Plus that kinetic energy. Well, I can even take those voltages and go one step further. I could actually say, hey, if I go final minus initial, then I could call it just a change in voltage. So the shortest way you can write this, you could say, hey, why don't we go with work equals, and then VB minus VA, we could just call that the change in voltage overall, and multiply that by your mystery Q, and then add on your kinetic energy. That's the nicest way to do this question. And again, this is a bit above and beyond. We don't have a lot of time this year, and I just wanted to show you this though as an option. If I arithmetically had to solve for that purple Q, wow, I like the equation that's in the box. They're giving me the work, right? It's right up there in the question. They're saying, oh yeah, by the way, here's how much work it is. And they're giving me the kinetic energy in the end, so I can put those values in. The only thing I wouldn't know is the delta V. So what would I have to do? Well, to find that delta V, I would need to go and first I'd have to find the voltage here, right? The total voltage at, get my pen working here, the total voltage at location A. We'd call that VA. Go and find that. Find the voltage from that pink 3.6 microcoulomb charge, find the voltage from that gray -2, and add the two voltages together. Just straight up add the numbers. Include any negatives, but straight up add the numbers. And then go and find the total voltage here. And then just subtract them. Just take that final voltage and subtract the initial voltage. And it could be a shortcut for trying to work through this question. We're going to call that above and beyond this year. Not going to see anything on any tests like that. Just wanted to show you that sometimes if you collapse everything down to talking about voltages multiplied by Qs, you can make the arithmetic really, really nice. The main focus of the lesson is actually this topic here, parallel plates. What we do in physics when we're trying to make a nice, even magnetic field or electric field is we take just sheets of metal and we attach a battery to them to charge them up. And so you're actually looking at those sheets kind of edge on. Okay, we looked at this picture a couple of lessons ago, and we're using this battery with some nice voltage to it. Right, so it's got some voltage label on it to make the top plate positive and the bottom plate negative. And if you were to put a little tiny, perhaps proton in here, then it definitely would get pushed around. It would get repelled by the positive plate and attracted to the negative plate, and it would get pushed down. Now, if you chose to put a negative charge in here, the opposite would happen. It would be repelled by the bottom plate and attracted to the top plate. So it would actually get pushed this way. So that's the force story for those Qs that get exposed to that environment. Well, let's go and put in the warning about field, right? Field just warns people about those forces, but we can't put both directions in. So we can only put one in, and we put in the direction for which way positives would get pushed. So here in blue, I'm just going to go and warn people, hey, look out, there's some electric field in here. Now the electric field does kind of bulge a little bit on the edges, but as long as you stay away from the edge, it's a pretty nice, clean, uniform electric field in there. Today's topic is not that picture because you've already drawn that. What we're going to need to know for finding the size of this electric field is the gap distance. So if you took a ruler and measured that gap, let's just call it D for distance. That's an important thing to know in order to find the electric field strength that's in here. So first, a few things, just kind of putting in here. That E field, that electric field, it is constant in two ways. It's constant in direction, unless you're right near the edge where it bulges just a little bit, so stay away from the edge. And it's constant in size. It has one value. And again, today's lesson is really about finding the size of that electric field. Probably the simplest equation of the chapter, actually. It says the electric field in between those plates is equal to the change in voltage from one plate to the other. That's just the voltage of the battery divided by the gap. Or if you want, if you prefer, you can rewrite that and say, okay, change in voltage is equal to the electric field multiplied by the gap. That's if you don't like fractions. Usually we write it in the orientation that you see on the left. Now, this equation, only use this for parallel plates. If you're using it in another application, it's probably not going to work out. And on your formula sheet, I've actually just stranded this equation kind of in the middle of the formula sheet, kind of away from the four corners of the chapter. It's just all on its own. I think it's even got a little box around it. Now, the fact that you can actually calculate electric field, and the units for that should be newtons per coulomb, right, for this electric field, by taking volts and dividing by meters, well, that's kind of interesting. That tells me that newtons per coulomb and volts per meter are actually identical units. So you can now use either unit system when you talk about electric field, right? They're absolutely the same thing. All right, so this story here, we've got a really big battery, right? So it's got a nice little label on it. It says, I am 400 volts. Great. And got my parallel plates, and apparently a very short person because the distance between the plates is only 12 centimeters. But there is a little person in there hanging on to a charge. The charge is positive. It's getting shoved down by that electric field, and the person is holding it up. So they're doing that applied force, the FA. And there are a couple of questions here. First one is, how strong is the electric field in that space between the plates? Okay, this is today's topic. So pretty easy. We're just going to take the change in voltage from one plate to the other. That looks like it would be 400 volts, and we're going to divide by the gap, 0.12 meters if we change it to meters. Now you get a whole bunch of repeating threes here, but to 3 sig figs, I got 3,330. Now, again, you have choice. You can go newtons per coulomb, or if you wish, you could go volts per meter, whatever you prefer. The direction for that electric field, well, which way would that little positive get pushed? The plates would push that positive down. The electric force is down, so that's what I would say. There's a downward electric field. Okay, well, what about that little person in there trying to move the proton from the floor to the ceiling, from the bottom plate to the top plate? The good news is the force is constant in this story. It's been a while since we've heard that, right? We've been doing all these questions for a couple of days where the forces were changing, but here they're constant. So we can go, hey, the work is just going to be the applied force multiplied by the distance. That applied force is the same size as the electric force, just a different direction, multiplied by the distance. And that electric force, well, if you're telling me the field, the whole idea is that that's a pre-calculator, so I can go QE in order to find out how much force there is, and then multiply that by the distance to find the actual total amount of work. So the Q would be 1.6 times 10 to the negative 19. I'm going to put the units in this time. Coulombs, that's for the proton, multiplied by an electric field of 3,330 newtons per coulomb. That would get me to force, and now I have to multiply by 0.12 meters. And that correctly calculates how much work is actually involved. The answer is 6.4 times 10 to the negative 17 joules. But before we leave this page, let's look at one little interesting issue here. What would happen to that answer, that 6.4 10 to the negative 17 joules, if we increase the spacing between the plates to 24 centimeters? Now, at first glance, you look at it and go, well, that 24 centimeters is showing up right here. And if you make that change from 12 centimeters to 24, you'd be doubling that D. And so you might expect the answer would double. But if you make that D 24 instead of 12, it would change the D here too. And that would actually make the electric field smaller by a factor of 2. So one part of the story is saying, oh, the answer gets smaller by a factor of 2. And the other part says, no, it's going to get bigger by a factor of 2. And those two issues, they cancel, they wash out, and it ends up being just the exact same answer. Another way to see that, what if we write this as, okay, we've got Q, right? I'm looking at this equation here, QED. The E was the change in voltage divided by the gap size, and then we multiplied by distance. And yes, you can see that the D's cancel out, and the work is actually just the Q multiplied by the difference in voltage. Remember, voltage is just about telling you energy, right? So I just need to give it a little kick with the Q that's involved in this story, and then I can see exactly how much work that would be. All right. Let's take a look at this page here. Find the speed of an electron up at the top plate if it's released from rest from the bottom plate. This is actually the way that we launch electrons inside old classic tube televisions, those big gigantic televisions that are super heavy to carry. They actually have a little electron launching gun in the background. And let's go back to the previous picture here. So they take electrons near the negative plate and they release them right there. And then they end up here going super fast. They drill a little hole inside this top plate so that the electrons can actually go through with some speed. So you've basically built a little electron launching gun, and they'll come flying out of there really, really fast. So if you were to draw your electron, it would be up here. And it's going to be really, really moving with some velocity. We're going to see if we can figure out how fast that electron would be going when it's at that positive plate. So it's a very, very common question to look at. How fast will a charge be going when it gets to the other plate that it's being accelerated towards? And I want to show you two different ways to do it. And the last time we split our page, we had to say, oh, the idea on the left is all wrong. But actually, both of these are right. They both work. Option number 1, find the size of the electric field by going change in voltage divided by gap. We already did that, and we found that it was 3,330 newtons per coulomb, and the direction of that electric field was down, because protons would have been shoved down. Then go and find the force. Go and use that electric field. Go and do QE. So E's help you figure out F's, and V's, voltages, help you figure out EP's, potential energies. So you could use that electric field now. You could just take that number and put it in here, multiply by the Q for your electron, and the number ends up being, for force, 5.3 times 10 to the negative 16. And by now it would be newtons. And you'll have to change the direction because this is a negative charge. So we'll spin this around and say, oh, well, actually, electron would get shoved up. Then you would find the acceleration. Don't even worry about gravity. It's too small to worry about. Just take a look at that electric force, that 5.3 number, and it can go in here for F net. And then the acceleration ends up being 5.9 times 10 to the 14. The units, of course, would be meters per second squared. And that would be upward. So the electron's going to get accelerated up to that upper positive plate. And then the final velocity. I would just do kinematics. There is no VI, so it ends up being VF squared is equal to 2AD. And when you run the numbers, that final velocity ends up being 1.2 times 10 to the 7 meters per second. Now, here's a better way to do this. This is the final little calculation for the chapter. We're going to do what I like to call a plate-to-plate calculation. as long as your charge that you're trying to accelerate is allowed to go all the way from one plate to the other, then it's going to receive the full voltage, so to speak. So we've got a story where we have a positive plate and there's a negative plate. And we've got this battery out here with this voltage label on it. So it's basically telling you how much energy it's going to get, right? Voltage is so close to being energy. And we're going to take our electron and we're going to release the electron right here. And we're going to watch and see how fast it goes when it crashes into that top positive plate. The fastest way to do this story is conservation of energy. And don't even worry about pluses and minuses here. I can look at this picture and see that, oh yeah, it'll definitely be going fast when it's up near that positive plate. So I'm not going to worry about any negatives. There's kind of a triple negative and one term supposed to be on the other side of the equation, and it's just overly complicated to do that. Let's just go with the values. We've got potential energy from the battery getting converted over to kinetic energy. The potential energy, hey, if you've got that voltage right there on the battery, they're pretty much telling you the potential energy. We just have to go and multiply by the Q that we want to use. And then kinetic energy, of course, 1/2 m little v squared. So you can find that 1.2 10 to the 7 number super fast by just saying, okay, how much charge have we got? 1.6 times 10 to the negative 19 coulombs. Now I know it's negative. Don't worry about that. Just looking at this story, I can see that that electron's going to pick up speed. So I can just take values here. I'm going to multiply that by 400 volts, which are actually joules of energy per coulomb. And I'm ignoring the negative sign on this plate-to-plate calculation because I simply want to find how much energy we've got. And that's going to get converted into going fast. So 1/2, make sure you grab the right mass. An electron is a lot lighter than a proton, so it's going to go really fast. So I got to grab that light mass, 9.11 10 to the negative 31, and then speed squared. So do two v's in this equation, a capital V for voltage and a lowercase v for velocity. And that velocity ends up being, as we already know, 1.2 times 10 to the 7 meters per second. So that's where we use some parallel plates to launch a charge. We've launched an electron by letting it go near the negative plate. We could have also released a little proton at the top plate, and then by the time it got down here, it would be going really, really fast. And you would be basically doing the same math to find its speed. It would be the exact same amount of energy. That whole left-hand side of the story here would be the same number of joules. But the proton would have a different mass. It would be a bigger mass, so it would actually have a lower speed in the end. So same energy, but a different speed. And that finishes up parallel plates, and it also finishes up Chapter 5, electrostatics.